Good morning. Uh, we're going to expand the general linear model this week. And the first thing that we're going to do is we're going to take a look at multiple regression when the predictor variables are no longer nice continuous variables, things that are measured on a ratio or an interval scale. What we're going to do is we're going to look at categorical predictors, things that are group membership. So for example, anything that's done in like a random sample design, an experimental design where you have a control group and an experimental group, we can call group an independent variable, and then the values of group are 0 for the control group, 1 for the experimental group, or 2 for another experimental group. So we can have as many groups as we want, but they're categorical, control versus experimental. And the matrix algebra doesn't care if your variables are continuous or if they're discrete. It doesn't care if they are measured on an interval scale or if they're measured on a nominal scale. It's all regression. And so today what we're going to do is we're going to take our friend spaghetti data that we used with the two-sample t-test, and we're going to show you that the matrix algebra and the for multiple linear regression and the two-sample t-test are the same thing. It's all just regression. And then we're going to take this and we're going to use this idea of multiple linear regression as the model for the rest of the semester. It's the model, the general linear model that we're going to use. So let me share my screen and we'll just get right to it, and I'll shut up. Okay, there's our Matlab. So what I've done is I've taken our data. Okay, remember when I took I took a package of spaghetti and we pulled out 10 strands of spaghetti at random, okay? And we call that our control group, okay? Our control group. And I label this 0. It's called a dummy variable. 0 doesn't mean that there's zero groupness to it. It just means that this is the control group, okay? And then we measured the displacement of that cantilever beam, that piece of spaghetti, until it broke, okay, in centimeters. Then we took another sample of 10 at random. We call that our experimental sample, and we dummy code that as a 1. That distinguishes the control group from the experimental group. And we did exactly the same thing, except I heat treated these, right? I took that lighter and I heat treated them for about 3 seconds. And what we're wondering is, did that heat treatment soften those enough and make them maybe a little tougher and not as brittle as the original sample? And so we did this as a two-sample t-test, comparing the mean of the control group with the mean of the experimental group. And so we're going to do exactly the same thing here, only we're going to use the matrix algebra of multiple linear regression. So the first thing we're going to do is, let's do it this way. I'm going to create a vector of outcomes, okay, a vector of our dependent variable. I'm going to go not there. I'm going to go to Matlab. I put a new variable in and I just paste that into Matlab, and then I will label that variable y, okay? And then what we're going to do is I will go back to here. I'm going to take my group membership, right, the predictor variable, the independent variable, and go to Matlab, and I'm going to put a new variable, and I'm going to put this in column 2, okay, my control group and my experimental group. And then I've got to make and I'm going to label this X. Okay, label that X. But I've got to make an augmented matrix. Remember, with multiple linear regression, we have to have these 1s in this column so that we can compute the intercept, right? And also count the length of these vectors to make it so that we can have n to be able to compute the means and the degrees of freedom. So what we're going to do is we're going to say X 1, not that 1, equals 1s, okay? And that just fills that first column with 1s. So this is our predictor matrix. Again, what we're trying to do is we're going to say is do all of the displacements in the control group, are they different or equal to those from the experimental group, okay? And if you remember the matrix algebra, what we're going to go a little slower. First thing we're going to do is we're going to go what I'm going to do is I'm going to make a matrix that is X transpose X. So I'm just going to call it XTX to make it easier to remember what it is. But it's X transpose right here times X. Now think about in your matrix algebra, what's going to happen with that? I'm going to take this matrix, this X matrix, and I'm squaring it. So it creates a square, I'm going to multiply it by itself. Okay? Left multiplication. I'm going to multiply it by itself. So what I'm going to get, every cell in this new matrix that I have, it's going to be a 2x2 matrix, is going to have, will be a sum of squares. Okay? It's going to multiply values of X times values of X squared, and then it's going to sum it. So that's how you get a sum of squares in matrix algebra. Okay, boom. And if we take a look at XTX, okay, you see that there were the sum of all the ones times 1, I get 20 because there are the length of that matrix is 20. The column length is 20. There are 20 measurements. Okay. This is going to be the sum of the column of 1s times the values of our variables, the 0s and 1s in our group membership, and then this one is going to be group membership squared, the sum of the group membership squared. So it's the sum of the squares. Okay. Now, and then from that, we're going to do. Let's just do the whole thing. Okay. And I'll do this XDX to the -1 times X transpose Y. Okay, this is going to give us our beta matrix. Oh, sorry, I have to multiply. This is Matlab. Okay. Okay. What I have here is, sorry, is not right. So sorry about that. You guys have never done this, have you? Okay. Gotta remember what's on. There we go. All right. I'm not squaring each one. I'm not multiplying each one or inverting each one. I am actually inverting the entire matrix. So I apologize for that. Okay. So we get beta. Okay. Now, if you notice at 5.38, that's actually the mean of our control group. And then the plus 0.4400, that is the mean, the difference in the mean of our experimental group and the control group. So if I take 5.38 plus and add 0.44, I get 5.82, and that's the mean of the experimental group. Okay, so beta gives us the means of our two groups. Okay? And we know in regression that our regression line will go through X bar, Y bar, right, of the two groups. Okay. All right. So now we've got our regression equation. Now what we can do is we have our prediction equation. We can use this to predict all those values. Now what we're going to do is we are going to look at our sum of squares, okay? The sum of the squares. And so I'm going to have to read off the formula, but the total sum of squares is going to be, first of all, I've got to calculate the mean of y. So y bar equals mean y. So that's the easiest way to do it. Okay, so I've got y bar right here, 5.6. Okay, that's the grand mean of all of our displacements to failure. Now what I can do is I can do the sum of squares total is going to be equal to, okay, y minus y bar, okay, prime times y minus y bar, okay, y minus y bar prime times y minus y bar. So you can see that's, again, it's a square, so we're going to get a sum of the squares of y minus y bar. Take every y minus y bar and square it and add it up, we get a sum of squares. That's the total sum of squares, the total variation in our dependent variable. Okay? Then we get an 8.68. Now what we'll do is we'll do the sum of squares regression. And that's going to be equal to, well, we have to calculate y hat first. We have to calculate our predicted values, okay? So we'll say y hat equals b 1, b 1, okay, plus b 2 times x 2. Okay, so what this is doing is saying this is our intercept. Okay, our beta matrix B here. That's our intercept. This is our slope. That's the 0.44 here. Okay, times the values in our data in our X file. Remember, the first column is R1, so the data is actually in column 2. So I get y hat. These are all my predicted values, and you'll notice it's the mean of the control group, and the mean of the predicted values are the mean of the control group and the mean of the experimental group, just like we said before. Okay, so we've got that. Now we're going to do the sum of the squares regression. So that's going to be the predicted value minus the actual value, excuse me, minus the y bar, sorry. Transpose times y hat minus y bar. Okay, and again, sum of the squares. I take all of the predicted values minus the mean, okay, and then I multiply that times all the predicted values minus mean, and add them all up, sum of the squared values. And that's our sum of the squares regression, okay? And we'll try to find the sum of the squares error, which will be the difference of those two. So sum of the squares error equals, that's going to be y hat minus y prime times y hat minus y. Okay, sum of the squares. These are the individual errors of measurement times the individual errors of measurement. So they're squaring, and we're adding them up. Okay, and that's our error. So the total variation is 8.68. The variation associated with our model is very small compared to that, about 1/10 of it, 0.968. And the error is very large. So not a very good model. Looks like my heat treating may not have worked. Let's take a look. We can find R squared, R squared equals SS reg divided by SS total. Okay. So we get R squared, and we see we're only accounting for about 11% of the variation. Is that making sense? That's awesome. Now, we can go through the whole thing and do the t-test, okay? But you'll notice that these are the values, the predicted values are the values of those groups, okay? And if I subtract those two and get their difference, that's the mean difference. Okay, that's actually this 0.44. That's the mean difference. That's the numerator of the t-test, right? And I can take the mean square error, which is the sum of the squares error, and I divide that by the degrees of freedom. Okay, so I can get the degrees of freedom are the number of pairs minus 1. So we have 20 pairs, okay, minus 2, excuse me. 20 pairs minus 2. So I've got length y, let's call it length y, minus 2. Make sure I've got length y minus 2. Okay. So I get the mean square error. And now I can say t is equal to SS, is equal to B2 divided by MS error. I get a t value, 1.02, pretty low. And I can then compare that to the critical value. Right? I can compare that to the critical value using ICDF, or I can look it up in a table. It turns out it's not significant. Now, let's run this using regress, which is easiest and faster. But I wanted to just show you that this is all the same. So let's take a look at regress. This is going to be B for the beta matrix, for the 95% confidence interval of the beta values, the residuals, the 95% confidence interval of the residuals, and stats. A bunch of stats that we like. And that's going to be regress y on x, comma. Okay, and I'm just putting alpha as 0.05 as a default for this. Okay, so as we take a look, what is B? Okay, that's from regress. You'll notice that the matrix algebra and regress are exactly the same. Right? If I look at in stats to find R squared that we calculated is exactly the same as R squared in stats. Okay. The F, this is the F value. Okay, so this is F. This gives us F and not T, but we can see that the F is about 2.26. The probability of F is about 0.15. It's not significant, just as we found with our t-test. And then it gives us the mean square error, 0.4284, the denominator of the F. Okay. And that's the denominator, that's the mean square error at T. I forgot I need to do, my T is incorrect. There we go. Sorry, I have to do the square root of that. The square root of the mean square error. Yeah, sorry. And T is actually even small, not very good. Okay. So you'll notice that all of those calculations that we made using the matrix algebra, that's exactly what Matlab does. And it turns out it's exactly the same as the two-sample t-test. It returns exactly the same values for the means, returns exactly the same value for the mean square error. It returns all those exact same values. And so the t-test, the two-sample t-test, is regression. And everything we do the rest of this semester is going to be taking this idea of regression and we'll just expand it. So instead of only two groups, control and experiment, we can expand it to however many experimental groups we want. We can have different levels of temperature or different amount of time in the annealing process. We can even have different types of materials. We can have spaghetti that's made out of semolina versus other sorts of rice flour and gluten-free stuff. We can change the material properties and we can look at as many predictor variables as we want using multiple regression. This is a really powerful model, but I want you to understand and think that, okay, it's very simple. All I'm doing is looking at these slopes, these partial slopes if we have multiple variables, and starting to say, does the variation that's explained by the independent variable, okay, does the variation in the dependent variable that's explained by the independent variable, is it significantly different from zero? And it's all the same. Okay, so that's the that's using the t-test and the and multiple regression as to show you that they are exactly the same. Okay, that's it for right now, and we'll follow up with a tutorial on how to actually do the analysis of variance, which is what you'll do because it's much more efficient over the long haul than using the procedures that I did in this video. Thank you.